Hi, I'm Alp. I'm a second year computer science student in Bilkent University. The goal of my physics project is to calculate the strain on oscillating cantilever beam. So my procedure is basically split into two stages. The first stage is the dimensional analysis, and the second stage is the experiment itself, the oscillation. First stage, dimensional analysis, basically means that you have to measure every dimension of the cantilever itself, meaning, for example, I've done it back in the lab and I measured the breadth of it using a Werner caliper, I measured the thickness of it using a micrometer, and I measured the length of it using a tape measure. So I noted the values in the lab and I made 5 trials to be completely sure that there is no unevenness in any part of the cantilever wood itself.
In the second part, we need a chronometer, a cantilever beam, its dimensions were determined in the first phase. Then we need a rope to tie the masses, we need a scissor to cut the rope, we need masses, and finally we need a heavy clamp object, like a printer. After tying the mass to the frame of the cantilever beam, we let it oscillate from its resting position. We gently drop it from its rest, and then wait 25 oscillations. When it makes 25 oscillations, we stop the clock. Similarly, the procedure should be repeated with different masses. However, it's important to note that there should be 5 trials for each mass. And also, if the cantilever beam is bent, it should be straightened up after every trial to ensure accuracy. From this point on, we have to use Young's modulus. Young's modulus is the stress over strain. So basically, we need to obtain strain, so we need to find the Young's modulus. In order to find the Young's modulus, we need to draw a mass versus period squared graph. So the period values that we obtained before will be useful. Now we need to take the mean of each of the 5 trials, and we need to square them, and we need to plot them in a graph versus each of the corresponding masses. So the slope of this graph will give us valuable information about Young's modulus. After finding the slope of the graph, our Young's modulus will be determined. This will be your experimental Young's modulus. The reason I'm saying experimental is because the cantilever beam itself has its theoretical Young's modulus. My cantilever beam is an MDF type. This MDF type has a different Young's modulus. Thus, we need to find an error percentage. Our percentage error is prominent and it was around 14%. However, we need to understand that this presence of this error is also mean that the strain value has also a margin of error. Since Young's modulus is stress over strain, our strain value also has an error. So first we need to calculate our strain values or expected strain values. That was our main goal in pursuing this experiment. So we find the values, then we'll find the theoretical strain values using the theoretical Young's modulus. Then we'll find the percentage error of our strain values. I believe that error has 4 main reasons, 2 of them being systematic and 2 of them being random. The first systematic error, I believe, is the swirling of the rope. As rope swirls around, it uses kinetic energy that the beam could have used to speed up. So the second one is the bend and deformation happening on the beam throughout the experiment. This will decrease the accuracy of the results. Moving on to the random errors, the first random error is the human reflex limitations. As I was both trying to keep track of the time and keep track of the oscillation number, it was hard, so it might have caused minute discrepancies in the data. The second random error is the initial acceleration I might have caused by releasing the cantilever beam. I tried to be as neutral as possible, but it might have happened, but will be really, really minute.